Good morning, guys. Going to continue with our acids and bases this week. I want to do a quick review with you first, show you one last thing with acids and bases, and then we'll be wrapping up acids and bases. Looks like we're going to have a quiz on Wednesday. So let's do a quick review. So you've learned that acids are anything when you put them in water, like HCl, form these ions right here, the hydrogen ions. So HCl is an acid. H2SO4, when you put it in water, it forms hydrogen ions. It is an acid. You learned that if you know the concentration of the acid itself, 0.2 molar in this example, you can easily determine the concentration of the hydrogen ions. So in this case, it's also 0.2 because of the 1-to-1 ratio. In the case of sulfuric acid down here, if we have 0.2 molar sulfuric acid and all of the hydrogen ionize, we get 2 hydrogens for every H2SO4, meaning the concentration of the hydrogen ions will be 0.4. So you learned you can determine the hydrogen ion concentration given the molarity of the solution. You also learn that bases are those things when put in water form hydroxide ions or OH ions. So in this case, sodium hydroxide is a base. When you put it in water, it forms hydroxide ions. Calcium hydroxide does the same thing. Just like with the acids, if you know the concentration of the solution itself, you can figure the concentration of the ion in that solution, in this case, a hydroxide ion. So 0.5 molar NaOH will have a concentration of 0.5 molar OHs. 0.5 molar CaOH2, because of the stoichiometry, will have a 1 molar concentration of hydroxide ions. So you learn the difference between acids and bases. You learned that we use the pH scale to quantify acids and bases. So you learn the equation for pH equals the negative log of the hydrogen ion concentration. So if you know the hydrogen ion concentration, you simply can plug it into this equation and solve for pH. You also learned that in aqueous solutions, or in water, the ionization constant is 1 times 10 to the negative 14th, which means if you take the hydrogen ion concentration times the hydroxide ion concentration, you will get 1 times 10 to the negative 14th. So using this ionization constant, you can solve for either one of these concentrations if you know the other one. So if you're given the hydroxide ion concentration, you can solve for the hydrogen ion concentration using this equation, and then plug the hydrogen ion concentration back into this equation and solve for pH. And lastly, you've learned that you can use the pH equation, pH equals a negative log of the hydrogen ion concentration, to solve for hydrogen ion concentration if you're given the pH. So if you're given the pH in a problem, you simply have to take the inverse log of the negative pH to solve for the hydrogen ion concentration. And there's 2 ways to punch that into your calculator. This is probably the easiest. Just type in 10 and then take it to your negative pH, whatever that is. Or you can have the calculator do that for you and type it into the calculator as inverse log of negative pH. Either way, it comes out to be the same thing. So again, you can solve for hydrogen ion concentration given the pH. Okay, the last thing we want to do then is we want to go over what's called POH. Essentially, it's the same thing as pH, except for just the opposite. So we typically use the pH scale, but there is a pOH scale as well, and it's just the opposite of the pH scale. So let's take a look at how the pOH works. We'll just use an example. We already know that pH equals the negative log of the hydrogen ion concentration. So pOH equals the negative log of the hydroxide ion concentration. So let's say that we have a solution where the hydroxide ion concentration is equal to, let's go 0.001 molar. So if we take the negative log of 0.001, we'll get pH. So pH is going to equal 3. We can do that one in our head. We're just moving it over 1, 2, 3. So pH equals 3. All right? pOH essentially is the same thing, except for we just need to take the negative log of the hydroxide ion concentration. Well, if we know the hydrogen ion concentration, we configure the OH concentration. We know using the ionization constant that the concentration of the OH is going to equal 1 times 10 to the negative 14th divided by our hydrogen ion concentration, which in this case is 0.001. So if we solve for that, we'll get, I'm sure the calculator will show you as 1 times 10 to the negative 11th, or its point with a whole bunch of zeros, 1. And if we take the negative log of this number to get our pOH, we'll get a pOH equal to 11. So if you look at these two numbers, pH and pOH, and you add them together, you get 14. The pH and the pOH always add up to that exponent in the ionization constant, or at least the opposite sign to that, because we're taking the negative logs to solve for these two. So pH and pOH added together equals 14. So how does using the pOH scale help us? And it just makes things a little easier if you understand the pOH scale as well as the pH scale. You wouldn't have to use pOH unless the problem specifically asks you to solve for it. Well, let's just do an example to show you how it might help you solve the problem. So let's say that you're given a solution that has a pH of 5, and the question's asking you, okay, well, what is the OH concentration? And maybe it's asking you what is the H and the OH concentration. So you can use the pOH scale to help you do that fairly quickly. If we knew that the pH is 5 and we know that 5, the pH plus whatever the pOH is, has to add up to 14, we immediately know that the pOH is 9. So if the pOH is 9, we can solve for OH very quickly, concentration of OH. It's just 10 to the negative pOH. So 10 to the negative 9. And you're done. So if you know the pH to be 5, you can quickly determine the concentration of the OH concentration. Just figure out what the pOH is, take the inverse log of it, or take the 10 to the negative pOH. The pH isn't always going to be nice, whole numbers like that, like a 5. So let's just try another one. Let's say the pH is 4.5. You do the same thing, 4.5 plus the pOH is going to equal 14. So we know that the pOH is 9.5 because 9.5 plus 4.5 equals 14. So real quickly we can solve for OH concentration. It equals 10 to the negative 9.5. And since we have calculators that you can punch that into, you could punch that into your calculator real quick and you get 3.16 times 10 to the negative 10 is what that number actually is. So you can very quickly find the concentrations of the OH as well as the H if we wanted to. Okay, let's summarize real quick then. And if you know these things on this slide right here, then you can solve a variety of pH problems and acid-base problems. So we know that pH equals a negative log of the hydrogen ion concentration. We can use the hydrogen ion concentration, or we can use the pH, to find the hydrogen ion concentration just using the inverse log of the negative pH. The POH equals a negative log of the hydroxide ion concentration. We can find hydroxide ion concentration taking 10 to the negative POH. We know that the ionization constant of aqueous solutions is 1 times 10 to the negative 14th. So the hydrogen ion concentration times the hydroxide ion concentration always equals 10 to the negative 14th. And if we're working with pH and POH, those two add up to 14. So you can use all of these things to solve a variety of acid-base pH type problems. Okay, you're going to get a few problems to work today. You'll have to incorporate all of these into solving these various problems. Good luck.